So in this video, we're going to look at the thermodynamic potentials, the internal energy, the Gibbs free energy, Helmholtz free energy, etc., etc. Okay, and the enthalpy, and in fact the chemical potential. And these are all related to each other via Legendre transformations, which we won't go into. We won't go into what a Legendre transformation is. If you know about Legendre transformations, you can read about how these are related to each other via that particular transformation. Okay, we're going to introduce them in a more physical way. So let's look first at the equilibrium of a thermally and mechanically isolated system. So by thermally isolated, we mean there's no possibility of entropy changing, and mechanically we mean we're not going to do any work on it. It's not going to do any work. Okay? So, the first thing we do is we write down the first law. Okay, du is dq minus dw, just conservation of energy. And then we introduce the second law, which according to Clausius can be written as dq is less than or equal to the change in temperature times the change in entropy. So the amount of heat absorbed is less than or equal to T times the change in entropy. Okay, so we're going to combine those two laws, and when we do that, what we get is the following inequality. That means du is less than or equal to T ds minus dw, which is that one. So we get an inequality. Okay, what the hell does this mean? Well, this means that if we isolate the system thermally, so that's 0, and mechanically, so that's 0, it will always move such that du is less than or equal to 0. Okay? In other words, it tries to minimize its internal energy. Okay? So a system which is mechanically and thermally isolated, what it will do is it will try to minimize its energy, its internal energy. Okay? And that's exactly what you're familiar with in classical mechanics. If I have a particle in a potential, here's my potential here, U versus X, and I put the particle there, and I apply a little bit of friction just for fun, it will go down here and sit at the bottom of the well. Okay, it will always try and minimize its, locally at least, its energy. Okay, and you're absolutely familiar with this from classical mechanics. Okay, you will note this particular law involves doing two things. It combines the first law and the second law, because the usefulness of the first law is completely obvious, I think, to most people. There's conservation of energy. But then you say, well, what about the second law? Where do we use that? Well, we're going to use it a lot here. And we're always using it in its inequality form, which basically says that dq is less than or equal to TdS. So when you put those two together, you find something which you know already from classical mechanics or from common experience that systems, you want a system to relaxes to equilibrium by minimizing its energy. Okay. So that you already know, I hope. Now, for a reversible system, we can get from this thermodynamic potential, which we call the energy, the internal energy, we can get the pressure and temperature. So we know that du is equal to dq minus pdv, that's the first law, and dq, if it's reversible, is tds, and pdv is pretty obvious. Okay, so from this we can just directly read off that the pressure here must be equal to minus du dv at constant entropy, and the temperature is equal to du ds at constant volume. Okay, so the natural variables here for u are S, the entropy, and the volume. Okay, and if we do du dv, we get minus p, and if we do du ds, we get t. So you can automatically, from the equation for the energy, you can get up the pressure or the temperature of a system. Okay, one seems to call these the Maxwell Relations. I wouldn't call them the Maxwell Relations, and I don't think anyone else would either. Maxwell Relations tend to involve second derivatives of things, not first derivatives, but you know, we'll allow him to call them whatever he likes. But these are the relations which give you the pressure and temperature in terms of the energy. Okay. Right, so this particular one, the energy, is what's minimized if we have a system which is thermally isolated and mechanically isolated. Okay. That's good for some systems, but not all experiments that are conducted in that way. What do we minimize if we have a system at constant temperature and constant volume? So I take my system and I say, right, I'm going to fix the volume and fix the temperature. What does it do? Okay. Well, okay, we can again write our inequality, which we had for the previous case, which is du is less than or equal to TdS minus dW. And if T is constant, which we can do that, we can rearrange this and we'll get dW is less than or equal to minus the change in U minus TS. Okay. Now, if no work is done, which we're going to say V is constant, so dW is 0. Okay, so dW is 0. We can then say, well, I can just write that as 0 is less than or equal to minus delta U minus TS. Okay. And then we'll switch this around, multiply by minus 1, we switch the inequality sign around, and we get this equation. Delta U minus TS is less than or equal to 0. And so let's define a new function, which we call the Helmholtz free energy, which is A. Someone's written other things. Someone's written as F, but here it's written as A. A is U minus TS, and a mechanically isolated system, constant V, and proceeds at constant T to minimize A. Okay, the Helmholtz free energy. The condition of equilibrium is that A is a minimum. Okay, that's the condition of equilibrium. Okay, so if you have T and V constant, then you will minimize A. All right, so far so good. Let's look at an example of this. You know, what the hell does it mean? When you say this is minimized, it's minimized with respect to what? What's there to minimize? Okay. Well, what's there to minimize is it's minimized over all the free variables you have. So, for example, when we went back to the energy, if I have a particle in one dimension, what does it mean to be minimized? Well, it minimizes over u of x, it minimizes respect to x. So you have du dx equals 0. And so u is minimized with respect to our free variable, which is x. Okay. So if we go to this system, what do we have to minimize over? Well, let's give an example. An example I'm going to pick is the swelling of a polymer chain. So a polymer chain is just a sequence of links like this. Here's the links, all freely, different models for polymers, but we're going to take the freely jointed chain model, where it's just a whole series of links of length A, and it does a random walk. Okay? And so if you have n links of size A, and you dissolve it in a solvent, so there's solvent here, there's one chain dissolved in a solvent, and there are no interactions between the links, you find the size of your chain, which is roughly that size there, is given by roughly AN to the half. It goes as the number of steps to the half times the link length. This is the link length A. And that's typical for random walk, as we've seen before, and we will see many times again. Now, that's the case where you have no possible interactions. Now, if we put in interactions between the links, the chain swells. So what happens is we're going to put some local interactions. So between, say, this link here and this link here, there is some repulsive interaction. They're solid rods. They can't possibly occupy the same point in space. So if you have a polymer monomer and another polymer monomer, they will repel locally. Okay, if it's in a good solvent. And the thing will swell to some new size, which is bigger. Instead of R0, we have some size radius RF. It'll be some size like that. We want to calculate how big RF is. How do we do that? Well, what we're going to do is we're going to use the Helmholtz free energy for our chain. Okay. The first thing you need to do is figure out what the Helmholtz free energy is, that involves statistical mechanics. Okay, which goes beyond what we already know. Okay, but we're going to keep the volume of the system constant and the temperature constant. Okay, so the volume of our beaker, this isn't a beaker, here's a beaker. We've got one chain, just for simplicity, you've only got one chain with some solvent. And if it swells or deswells, it doesn't matter because the solvent takes up some space as well, so the volume is constant. So we're going to write the Helmholtz free energy as two terms. The first term is due to the stretching of the chain. So the chain, which is originally this big, has now swollen to that big. Okay, in terms of how big it is. The number of monomers has stayed the same, but it's swollen a bit. Okay, that involves somehow the chain expanding and stretching, and when it swells to a particular size R, the free energy you can calculate very easily. It's like a Hookean spring. It's 3 kBt, 3 on 2 kBt the size squared divided by Na squared, just like half kx squared. Basically, it's a Hookean spring. So if it swells to a size r, you get a extra part in the free energy, which is that. Of course, that particular term in the free energy, if we're going to minimize it, tells the system, look, don't swell, because as soon as you start swelling, R gets bigger, and I pay an energy, a Helmholtz free energy penalty. Not good. There's another term, however, which makes it swell, and that term is the term which says, look, this particular bit of chain here cannot occupy the same position in space as that part of the chain. Okay? And that involves binary collisions. If we count all the binary collisions and we associate with each of them a sort of volume, what you find is that this particular term in the free energy is n squared, which counts the binary conditions, kBt, the volume element, the size of the volume element of this thing, divided by the radius of my thing cubed, radius of my chain cubed. Okay, so we have two terms, that one and that one, competing here. One of them says make the thing smaller, one the other says make the thing bigger. Okay. So total free energy is just, total Helmholtz free energy is the sum of those two. And to get the size of the chain, all we do is we take this and we minimize over the only free parameter we have, which is R. So R can be anything we like, but we want to choose the minimum R. Helmholtz free energy says choose the minimum R. Just do dA dr equals 0. And we find, ignoring numerical prefactors, that R, the minimum, is at Rf, which is n to the 3/5 a squared v to the 1/5. And in particular, this n to the 3/5 law is what was seen experimentally by many, many different measurements. You can do hydrodynamic measurements to measure the size of these things, and do light scattering measurements. And when you put a chain in an environment which likes to swell up, this is the size. It scales as the number of monomers to the 3/5, which is sizable because n could be, for a chain, it could be 100, it could be 1,000, it could be 10,000, it could be 1,000,000. Okay, so it's a very, very sizable effect. And this theory, which we just wrote down, is due to Paul Flory, who won the Nobel Prize in 1974, a long, long time ago. Okay, and Paul Flory was in fact the postdoctoral supervisor of my PhD supervisor. Okay, so Paul Flory is now unfortunately dead. Okay, so that's an example of using the Helmholtz free energy. Okay, what's the natural variables for this free energy? Well, the definition of Helmholtz free energy is U minus Ts, and therefore dA is du minus Tds minus SdT, just differentiate this. But du is Tds minus Pdv, which is first law, and so we get dA is minus Pdv minus SdT, and so the natural variables for A are V and T, okay? And if you want to get the pressure, it's from here, it's pretty easy. P is minus dA dV, and the entropy is dA dt. I think there should be a negative sign there, unless I made a mistake. Okay, probably a negative sign. All right, so that's the Helmholtz free energy. Next one. Okay, we're gonna get the Gibbs free energy. So we're going to play the same game again as we just did, but here we're going to keep the temperature and the pressure constant. And if you do that and use the same algorithm we just did, use these inequalities, we can define the Gibbs free energy, and that is equal to the Helmholtz free energy plus PV, and that's what you minimize at constant temperature and constant pressure. Okay, I'm not going to derive that for you, but you can see if you go back and do the calculation, that's what you'll get. And if we do dg, we find it's dA plus PdV plus VdP, which turns out to be minus SdT plus VdP, and therefore at constant T and P, G is a minimum. Okay, so that's what it is. And then from this, you can just read off directly V must be equal to GdP, and S must be equal to minus dg dt. Okay, constant pressure. Okay, that's the Gibbs free energy. Now, there's not much point in doing the Gibbs free energy unless we actually do an example. Okay, and the example that's really important, it has many applications in physics, of course, but its real usefulness is in chemistry, because chemical reactions are often done at constant temperature and pressure, i.e. the temperature and pressure of the lab. Okay, so that's why this is so useful in chemistry, because you have The lab's at 25 degrees. There's an atmospheric pressure. So we're just going to use the Gibbs free energy to figure out what's going on. Now, the Gibbs free energy thing tells us, the chemical potential given by the Gibbs free energy tells us that G is, systems try to minimize G, okay? Try to minimize it, okay? What does that mean? Well, that means if your G for the products is less than your G for the reactants, then G has been lowered by the reaction, okay? And since the system tries to minimize G, the reaction will proceed. So if you have the products of a reaction, so you have, here we have reactants, goes to products. If this side has lower Gibbs free energy than that side, then the system will say, thank you very much, this is exactly what nature wants me to do, lower G, I will proceed, I will make this reaction go, okay? On the other hand, if it's the other way around, then the reaction will go backwards, okay? So let's do an example here, a really simple example, which is almost not even chemistry. It's just dissolving ammonium nitrate in water. So ammonium nitrate is this stuff, NH4NO3. It's a solid stuff. It's used as a fertilizer, of course, and if you do mix it with various other things, you can make an explosive out of it. Okay, and of course, that's done. In warfare, often ammonium nitrate is used as an explosive, or used to be. Okay, so what happens? We're going to take this stuff and dissolve it in water. So when it dissolves in water, here we go. I take some of this stuff. Here's my ammonium nitrate. This is ammonium here, and the nitrate bit. And then what is it? Breaks up into ammonium ions and nitrate ions. Okay, and there they are, floating around in water. So it's aqueous environment. So this is almost not a, as I say, not a chemical reaction, but it depends how far you're prepared to push chemistry. Anyway, you just take this stuff, throw it in water. What happens? Well, you can go and look up what the delta G is for this reaction in tables, and it turns out to be, if you can't look it up, you can certainly calculate it from the tables, minus 4.4 kilojoules per mole. Okay, that tells us, this negative sign here tells us something really important. The reaction, which is dissolution, proceeds spontaneously. It will just go. Okay, and so that tells us this reaction will happen. If you put ammonium nitrate in water, it will dissolve. Okay, it won't just, it doesn't spontaneously undissolve out of water and precipitate. Okay, so as an aside, you'll know there are these chemical tables in chemistry. Most of you must have done a lot of chemistry. And there are chemical tables which will give you G, and they'll give you H, and they'll give you S, or allow you to calculate all those things for different reactions. And the reason why those tables are possible is because those three things are state functions. They don't depend on how you get there. Okay? So it's really important that G, H, and S are seen are state functions. Otherwise, you couldn't have these tables. Otherwise, for instance, the idea of Gibbs free energy would be very, very useless in chemistry. Okay? G, H, and S are basically like the mass of, they're like the mass of oxygen. Okay? The mass of oxygen atom doesn't depend on how it got there. Okay? It's just the mass of an oxygen atom. So this is true for these potentials. Okay? So it's a very simple example of the Gibbs free energy in use. Okay? If delta G is negative, it proceeds. Okay. Now, we can play the same game again and derive the entropy. Not the entropy, the enthalpy. And this time we're going to keep the pressure constant and have no heat flow. Okay? That's not usually the case in chemical reactions, but we'll see that the enthalpy still is important in chemistry. Okay? So we met H before, I think, and H is U plus PV. So it turns out GH is TdS minus VdP if you do the calculation based on the first law. And H is the thing that's minimized at constant pressure with no heat flow. And from here you can derive, dH/ds must be T, and dH/P must be minus V. Okay, so you can get from those, you get the temperature and the volume. All right, natural variables here are obviously S and P for H. Okay, so why is H useful? Okay, the enthalpy. Okay, it's useful because it measures how much heat is absorbed in a process, in a chemical reaction, for example, or in a physical process. So, dH, by definition, is du plus PV. and that's equal to delta U plus P delta V. And why don't we have a V delta P? Well, we don't have a V delta P because we're going to have constant pressure for this system, okay, as you get in the lab, okay, which is dQ minus dW plus P delta V. But if we're only dealing with pressure work, i.e. there's no magnetism or any other kind of weird work, no electrostatic work going on, nothing else that's weird, then we have dW is PdV, and those two terms will cancel out. And so we have dH equals dQ. So dH, delta H, is a measure of how much heat is absorbed in a reaction, by the reaction itself. Okay, so now it becomes slightly tricky. It's only slightly tricky, but you've got to think about what this means. If delta H, which is the same as delta Q, is positive, heat is absorbed by a reaction and it's endothermic. Okay, so delta H is bigger than 0 means reaction is endothermic. Otherwise, if delta H is less than 0, it's exothermic. Okay, so as a summary, G determines if a chemical reaction goes forward, and H determines how much heat is given off. Okay, G is the important one in some sense, because G really says, is this a viable reaction? Okay, to some degree. Whereas H tells you basically how much heat you're going to get out or how much heat you have to put in. So let's do an example. We'll go back to our ammonium nitrate dissolution problem. Here it is. And from the tables, we find out for this reaction, I'm not going to show you how to use the tables because we're not doing a chemistry course, that delta H is 28 kilojoules per mole. Okay? So delta H is 28 kilojoules per mole. That means this reaction requires amount of heat per mole of 28 kilojoules to go forward. When it goes forward, that's how much heat it requires. So heat is absorbed by this system. It's endothermic. Okay? And unless you supply heat, dissolving ammonium nitrate in water will cool the water down. So you throw the ammonium nitrate in, and it will cool down. Okay, it's an endothermic reaction. Okay, so there are some reactions in chemistry, even the dissolution ones. You just mix, you put acid in water, it heats up, for example. That's exothermic, and DH, that kind of reaction will be negative. But here, DH is positive. It's endothermic. It absorbs heat. Okay. So our final our final thermodynamic potential is the chemical potential mu, which we will have a lot more to do with when we do with bosons and fermions. But chemical potential mu arises from something we haven't really allowed for before, which is to allow the number of particles in our system to change. So the first law is now written: du equals dq minus dw plus mu dn. Okay? And mu here is called the chemical potential. So this guy is the chemical potential. Okay? Invented by Gibbs himself. Okay? And similarly, you can go back and derive what change in Helmholtz free energy or Gibbs free energy is. Okay? And mu here is dA dn at constant V and T, or G dn at constant P and T, or du dn at constant V and Q. Okay? So, its usefulness is that it's the energy involved in adding a particle, and it's very useful in dealing with phase equilibria, where you have different coexisting phases. And one condition of equilibrium is that if you can exchange material, the chemical potentials must be equal in each coexisting phase. So if you have two phases, suppose here we've got phase 1 and phase 2, and I have some atoms of type A, the chemical potential of the atoms of type A here must be equal to the chemical potential of the atoms of type A here in this side. And similarly, if another atoms of type B, it must be like that. Okay, so this one could be nitrogen, A could be nitrogen, B could be oxygen. If you have two separate phases, one might be ice, one might be gas, say, for example, you've got to have the chemical potentials be equal for each species across the boundary, across the phase boundary. Okay, so one example, let's do a simple example of that. If we have, as I said here, in equilibrium, the chemical potentials of the same species must be equal. Okay, so let's take a case of liquid water in equilibrium with its vapor, which we will study quite soon. Okay, so you take a container at certain temperatures, you will find that you can have a liquid water, and it will have, suppose there's no air here, just water vapor, and those two things will be in equilibrium. Some of it constantly you'll have the vapor colliding with the liquid, and liquid bits coming out and forming the vapor. There'll be an equilibrium. There'll be some vapor and some liquid. Okay. What I just told you is the chemical potential of a water molecule must be the same here as it is here. Okay. And if you know the formulae for the chemical potential in each case, you can calculate, for instance, what must be the vapor pressure, etc. So mu liquid must equal mu gas. The chemical potential for each molecule must be the same in both cases, in both phases. Okay, that's a very simple hand waving situation. Now let's look at a more complicated calculation, which you've done before, or at least the problem you've done before. So you're familiar with the barometric problem, where you have an atmosphere which is isothermal, and there's a gravitational field G pointing down, and you have some molecules of mass M, and you want to figure out what the density of this system is as a function of height Z. Okay, and I'm pretty sure most of you will have seen this problem before. We're going to attack it by using chemical potential. Now later on, I hope we will see that the chemical potential of an ideal gas is very simple. It's just a constant plus kBT times the log of the number of molecules per unit volume, which of course means it's still the kBT times the log of the pressure or log of the density or whatever. Okay, but here we're going to use number of molecules per unit volume. Okay, and you might say, oh, you can't take n log n here because it's not dimensionless, but of course all the dimensionless stuff is shoved back into here. Okay, so that thing still is fine. Now, mu is the energy needed to add up one particle. So in a gravitational field at height Z for a molecule of mass M, all we have to do is add the extra term to do with the gravitational field, which is the mass of the particle times G times Z. So that's our formula for the chemical potential everywhere in our column of gas. Okay, constant temperature. Now, we know that the chemical potential must be equal everywhere, because this molecule here can go down to here, and this molecule here can go up to there. And so we know that mu at Z1 must equal mu at Z2 for all Z1 and Z2. In particular, we know that mu at Z must equal mu of Z plus dZ, or that d mu dz is equal to 0. There's no dependence of mu on Z. You can't have that because they can freely exchange amongst different Z's. And when you put those things together, using this formula, what you find automatically is that the density equals the density at some point, which is, in fact, this is the density at ground level at Z equals 0, x with minus mgz on kBT. And that's the barometric formula, which you are all familiar with, probably from doing the problem in actually different ways to this. But that shows the power of the chemical potential. It is quite